3, 2, 1, live, Achtung, Robert. Next talk, and now I think I'm going to be joined by Robert Pucher. Robert, can you already hear me?
Yes, I can hear you.
Very welcome. I guess you are in Vienna at the moment, is this correct?
At the moment, I'm in Vienna, not in the university, but at home.
Then let's call it home office for today.
Yes, due to the COVID-19 restrictions we have now, unfortunately.
Well, and today you're going to talk about user experience and the human mind, and which is a very rich field of user experience in general. By the way, Robert is the program director of software and engineering at the Vienna FH Technicum, and I think it's going to be very interesting around 25 minutes. He has more than 30 years of experience in his field, and Robert, here is your stage, 25 minutes to go. Enjoy.
Thank you very much. Good morning, afternoon, good afternoon, ladies and gentlemen. I'm happy to give the talk here at the World Usability Congress 2020. Unfortunately, it's online. I prefer face-to-face. However, I'm happy to have the technical opportunity to do it. I'm talking about user experience and the human mind. Why? Of course, all users have a brain, and the brain basically shapes our experience. So to my experience, it's more important to know how the brain works and what people do with their brains to get a rich user experience. It's absolutely pointless to emphasize on technical issues only and not onto the human mind. Let's start with this image. Please set the time to 10:50 a.m. on that machine. How can you do that? Give yourself some seconds. Maybe it's that, maybe it's that, maybe it's that. What does that icon mean? The real problem is that I showed this image to many people for years now, and nobody could set the time. Nobody could set the time, neither me. We never could set the time on this microwave oven, what it is. But then somebody found a solution. He said, wait until midnight, switch the electricity off, switch the electricity on again, and it will start with 000, and then the time is correct. This was the only way to set the time. But why is that so complicated? Why is it so complicated? It's simple. It's not overloaded with information. It's simple icons, but nobody understands what the icon means. And the reason for that really lies within the human brain. Oh, what's happening here? Here are some numbers showing up. 1805, for example. Well, don't pay too much attention to these numbers, please. So this is the human brain. When you see the human brain on an MR scan, you can see that it's a huge structure inside the skull, folded into highly folded to get about 2 square meters of surface into the skull. And when one starts to count what's inside the human brain, you easily find that you have about 68 billions of so-called neurons. This is quite a lot of number. This is quite a huge number. And you have additional 84 billions plus minus 10 billions supporting cells. And maybe interesting, only 19% of these neurons are located here in that area of the brain, which we used to think. Much more of the neurons are located here in that part of the brain we use to coordinate our movements. So this is a very complicated part also. Basically, the brain consists of these neurons. And when you go on and you want to see some to see some numbers and scales and circuits in the brain, you see the basic element is the neuron, which is 10 to the power of minus 6 meter. If you go down to 10 to the power of minus 5 meters, you find circuits in the brain. If you go down to the 10 to the power of minus 4 meter, this is the size of a pixel, for example, on a TV screen, you find networks in the brain. When you are in the area of 10 to the power of minus 7 meters, you find the switching elements of the brain. There's a huge number of switching elements. When you go to 10 to the power of minus 2 meter, you find parts of the brain, and these parts of the brain are very specific for different things the brain does, and so on and so on. If you go to the very small size of 10 to the power of minus 8 meter, you will find that the electric part of the brain is going to be supplemented, or when electric signal is transmitted, it comes to chemical transmission of signals. So it's a very interesting structure. And one of the most interesting points is that the parts of the brain are the software. So we are here in that part, basically, where we experience the sensation of I am. If you watch your hands, for example, or if you watch the computer screen now, or if you think about your body, or if you think about whatever you did in the last 5 minutes or long ago, this happens here, basically. That part of the brain is responsible for movements, and that part of the brain is responsible for perceiving visual information. Well, and there are many of these parts. So nowadays, you are even able to monitor a brain function in real time. And you can see the different brain areas are used for English reading and for Chinese reading. And again, different parts of the brain are used for Chinese writing, but very different parts are used for English writing. So the process of writing and reading in different languages is totally different. And it's very difficult to talk about people are like this or that, because people, depending on their individual background, have a very different brain, and the brain functions in a very different way. So probably one of the most important things in human beings is that everybody is individual. You won't find two persons thinking the same thing, even if it goes down to very basic things like a chair or whatever. Okay. Oh, again, that pops a number up. It's 1805. Don't pay attention to this 1805. Nowadays, it's even possible to measure this brain activity here by fMRI imaging and reconstruct what people are seeing. So the knowledge of how the brain works is quite interesting. For example, this was the person seeing, and this is what was reconstructed by just measuring activity in the brain, non-invasively, of course. It's not done by putting electrodes in, it's done by measuring blood flow, basically. And it's interesting that you can distinguish between these images. And this is what Chinese researchers did some years ago, 2 years ago. But the human brain has a huge bottleneck. This is something one really has to keep in mind when it comes to information processing. And the bottleneck starts with the neurons itself. The whole human mind is based on these fundamental elements, the neurons. And the upper limiting frequency of a neuron, the maximum frequency a neuron can switch on and off and on and off, is 1 kilohertz. So 1,000 times per second. It's the maximum frequency. Let's compare this to your smartphone. Your smartphone runs on some gigahertz, which is when you compare 1,000,000 times faster than the neurons in a brain. However, the structure is completely different. In your smartphone, you have probably 6 to 8 processors, and the adult human brain contains 68 billions of processors. The human brain is capable of doing 10 to the power of 17. This is a number with 17 zeros, bit operations per second. You have to keep in mind that this is a huge number. It's a huge number. It's comparable to computing centers with thousands of fast CPUs. It's comparable to supercomputers still today. And we only need 60 watts of energy for maintaining that. But this is a bottleneck. Again, 1805. Probably you can, if you try, but 1805, what does it mean in that context? Let's forget about that. When we talk about speed, you might argue speed is the most important factor. If you look at this cat here, and the boy is standing here without any protection, and the cat is maybe approaching the boy. But these type of cats usually don't attack humans, so it's not dangerous. It's not really that dangerous. If you have a cat like this in such a situation, you're probably dead. So you might say power is the most important factor. But what is really the more important factor? When it comes to evolution, you find that our vision system tries to extract the meaning of objects around one. So if you look here, there's grass, it seems to be hot, there's water, you might be able to drink it. There are animals, you know they're not going to attack you. And now is the question, how do you know that these animals are not going to attack you? You took it from memory. You learned it for years and years, and you took it from memory. And this influences user experience a lot. Most information is taken from memory and isn't taken from visual perception. What should I do now to achieve my goals? That's the question we always ask. What should I do now? How should I use my resources to achieve my goals? Do I experience any danger? Can I proceed? What can I do? How can I go on? Let's look this up in that image. German Shepherds perceive a complete different mental image of the dog than people who, for example, did grow up with a German Shepherd. They have a complete different mental model of this animal in their mind. If you look at this dog here, you easily can see that the dog is not aggressive, if you know what I'm talking about, but only if you know how a German Shepherd behaves. Oh, again, this number, 1805. What does it mean? 1805. Anyway, don't pay attention to that number. So what people did for years now, they began in the 70s, and it's quite advanced now. They simulate how the human perception system processes information and how the actions humans do actually can be estimated from the visual input. And sorry, and this is something I really want to explain you in more detail. The visual input is somehow directly put to an action selection without even knowing much, without even much pre-processing. Well, there's some pre-processing. Imagine you're standing in front of a snake. You immediately feel fear, and you would try to flee. So this is done without involving your working memory. This is the part of your brain, the working memory, where you experience the sensation of I am. So the information is encoded. The system works quite complex. You have action selection, you have attention selection, the working memory, which is in your mind, of course, is selected externally. Also, imagine you're driving a car and you suddenly spot a police car close to you. Of course, your attention is focused on the police car. What is the police doing? Are they taking care of me? What, and so on and so on. So there's a lot of attention selection without being aware of what you do. And in the end, there comes an output and people do things. And the very important thing from here to here, is a data compression, which is in the range from 10 to the power of 7 to 1. So the data compression, which is done here, is huge. We manipulate very few elements in our working memory, but we perceive a lot more. So please keep in mind that 90% of what we do is in a subconscious mind. So visual input doesn't equal working memory, and working memory doesn't equal action selection. This is one of the most important things I want to tell you. Visual input does not equal working memory, so you don't know what you actually see, and you see different things which are not here. And the action selection, what you finally decide to do, is not done by the working memory, but it's done by a different part of the brain. What happens if you compress data to a high amount? What happens if you compress data to a high amount? The risk, what is the meaning of objects of one, is quite complicated. If you compress everything down to that part of the elephant, you might believe an elephant is like a rope. Or if you are far away, you might say an elephant is soft and mushy. Or you might say an elephant is like a snake. All of these people are correct, but they don't perceive reality. Well, again, 1805, whatever that means. So to come back to your working memory, just keep in mind 10% of what you perceive, what you see, comes from your sensory system, and 90% is taken out mostly directly from memory. When you look around, it's hard to believe that it's like this. And there are quite a lot of ways to tell this is correct. One example is if you look to the cross section of a human eye, okay, you will see there's an image. In that part of the human eye, you really can see with high precision. But in that part of the human eye, you can see movements. Probably you notice that movement. Even if the movement is not in the center of the screen, you notice it because your visual system puts the attention on that and tells you, look, this might be a danger. Okay. Oh, again, 1805. I don't know what that means. To put it in other words, when you see an image here, only that part of the image you can really see. And if you see that image here, you might see that, and all of that area is just taken from memory. It's not perceived, not even if you directly look in it. And this makes user experience quite complicated. Look at that image. Is it complicated? Yes or no? Most people say yes. But if you ask to an air traffic controller, he says it's very simple. Everything you need to know is on the image. Why does he say that? Obviously, because the mental model, the mental representation of that in an air traffic controller differs a lot from our mental representation. I show you a simple example. Take 5 seconds and tell me, how can you switch or make the temperature to be warmer? What do you do with this control to make the temperature warmer? About 30% of people here in Austria tend to say you have to turn the knob to the right, just because they take the mental model from their car to that image, which is absolutely wrong. You have to switch off the air condition, or you have to put this to 0. Then it's becoming warmer inside the car if you have that type of mental model. What is this? I only did show you for a short time. I show you again. Only parachutes, only people who jump with parachutes know that this means this is a fully deployed parachute which doesn't have any more function. So this depends on the representation on what people have learned. So keep in mind, everything one perceives or thinks only exists in an unrealistic, simplified model of the world. We have limited computing resources. We have 10 billion bits per second, which are inputted by our eyes. The model of reality we have in our working memory is approximately only 100 bits per second. This means a compression of data from sensors to working memory of 10 to the power of 7 to 1. What are the results of that? A very simple thing is, Anna explains Bert what she intends to do. This is what Anna means. This is what Bert understands. Why? His mental representation is that part. Anna's mental representation is that part. Whatever Anna is talking about that area, it might be, Anna might be a brain surgeon, Bert cannot understand because he doesn't have that knowledge, and vice versa. And this is the problem most designers have when they come to real world problems. This is just around the corner here in Vienna. This is what the designer planned. This is the real world in the designer's mind. And this is the behavior of the users in the real world. So this you experience everywhere. What did you see? I go back. What did you see? Did you see it's Ryanair? Did you see that Vienna to Faro was the last trip looked up here for 2 people? Or did you see our health measures for safe travel? Or did you see flights of the day? It really depends on what you were focused on or where you looked at it just at the moment being. Please cancel the reservation. Please cancel the reservation. What what do you need to do? Nobody understands that. This was done with a huge budget by the Austrian Federal Railway System. In fact, you have to click here, which doesn't correspond to that button. Everybody who has to do with design knows that this doesn't work. But why did they do that? That's a very interesting question. So again, 1805. Or now I'm slowly running out of time. So I come to some strategies. Strategies to make information easy to perceive, for example, can be, what is the exact context of use, if you ask? What mental models does the user have? Too much information at the first glance? And most important, meaning of the perceived objects in relation to my intentions, verify by measurement, verify by measurement, verify by measurement, usability test or something like this. When do I arrive? When you look at the screen. You had the screen for quite a while. Obviously, you have seen the arrival date is late. It's 8:37 and not 8:36 as it's supposed to be. Everybody understands that. But now I'm the conductor and ask you on the same screen, please show me your ticket. Usually people here need much longer because the show ticket button is not associated as a show ticket button. So obviously this never was tested to the extent it was necessary to do. Other strategies include subconscious control of attention is important. Of course, everybody looks into the face of this baby. Babies are attractive, babies look at you, so you look into the face to find out what the baby means. Not many people look onto what they are supposed to look at. But what happens if you turn the face of the baby into that direction? Most people also look here. This is because we follow the path of what the baby looks at to find out what's the meaning for the baby. So there's an inbuilt model in our brain which forces us to look here. It forces us to look here. Okay? So a face always will attract attention, but be sure the face is looking at what you want the viewer to see. Or attention, attention, attention. One of the most proven ways to draw an audience is by introducing a knowledge gap. Conversation myth busting, common misconcepts that are killing your landing page. You can easily find out that if we need to get more information to find out what the other means, we are engaged. We are really, really engaged. Or strategies improve the customer engagement by tackling the decision paralysis. We have very slow minds. There's too much to decide. One thing is, if you ask what's for dinner, nobody can answer you that question. We have all been there. But nowadays, the obvious strategic choice is to simplify the number of available options. But now, today, consumers demand personalization. And so it's very easy to take the personalization and to find what people and guide people through the experience. You can look up many of these strategies in many ways. For example, people don't like to be idle or any other things. Or persuasive design frameworks. Persuasive design frameworks avoid the way people also get bad feelings. Or the endowed progress effect. And there's one thing I want to point out in the end. You always have the problem when it comes to software that you have developers and you have UX design, and there's a war between the two worlds. So one of the most important things to make that work is to find teams who work together with teams to finally bring all the knowledge you got into a product. Here again is one number, 1805, okay? Let's go on. I go to the last point. Can you remember a number from the first screen? Probably yes. It's 1805. Repetition, of course, forces your brain to be attentive. And repetition forces you to remember things. This also is something I wanted to share with you. Thank you for your attention.
Well, thank you very much, Robert, here for giving us this very interesting talk about what's going on in our mind, actually. But finally, is there something behind it using this 1805 number, or is it just a random number?
It's a random number. It's actually my birthday, 18th of May, so I remember it easily.
Okay, because like that was the question I think and you were trying to let us ask this, right? This was the intention behind it.
I just wanted to try to show you that when you see a number repeatedly, first you remember it, and second, because there's no meaning in it, you're going to assign meaning to it. But the meaning you assign is the meaning you assign. You don't know the meaning, but in the end, you remember that number, even if it's meaningless.
Okay, so, inverted psychology.
To push things into, but everybody uses that to some extent. To push something into the mind of people, you need repetitions. If they're repeating facts, our mind says, oh, that's important. I should remember that. Maybe I can need that.
Okay. Well, Robert, thank you very much here for joining us at the World Usability Congress. These were your 25 to 30 minutes at your very enlightening talk about user experience and the human mind. If you want to get connected with the speaker, you can do so, of course, here in the live discussion or directly on the Swapcard website, or I guess Robert Pucher, you can just put in on LinkedIn. Thank you very much, Robert, anyways, here for joining us and for giving us this enlightening talk.
Thank you. Bye-bye.
Goodbye. See you, Robert. And in a few seconds, we're going to continue.